Ever wonder how your speakers can perfectly separate the deep thump of the bass from the crisp hiss of a cymbal? Or how a radio can pick out one single station from a sea of thousands? Well, the secret to all of that lies in a concept that's a little more complex than simple resistance. Today, we're going to pull back the curtain and demystify electrical impedance.
Visit youtube.com/avidsystem and don't forget to subscribe.
Okay, so before we dive into the deep end with impedance, let's start with something we're all familiar with, right? Let's talk about its simpler cousin. In the world of direct current, or DC circuits, like a battery and a light bulb, the whole idea of opposition is super straightforward.
Right, so with DC, the current flows in one direction, and the only thing pushing back is good old resistance. Easy peasy. But our homes, the power grid, most of our cool gadgets, they run on alternating current, AC, where the electricity is flipping back and forth dozens of times a second. So what happens to the opposition then? Does it stay the same?
Yeah, this slide pretty much nails the whole problem, doesn't it? In the simple DC world, opposition is just resistance, which we call R. But over in the AC world, we know resistance is there, but it's not the whole story. That big question mark? That's exactly what we're here to figure out.
So let's crack this case. This total, combined, more complicated opposition that shows up in AC circuits, well, it has a name. And understanding it is the key to unlocking how so much of our modern technology actually works.
And that name is impedance. We use the letter Z to represent it. You can basically think of it as the complete picture, the total opposition in an AC circuit. And just like resistance, we measure it in the same unit, ohms.
But here's the twist. Impedance isn't just one single thing. Nope, it's actually a combination of two very different kinds of opposition working together. So let's meet the two key players in this story, resistance and a new character called reactance.
So impedance has two components. First, you've got the usual suspect, resistance, our old friend R. This is the part that fights the current and turns electrical energy into heat. But then we have this new kid on the block, reactance, or X. And reactance is different. It doesn't just waste energy as heat. It's more like a spring. It stores energy for a moment and then releases it right back into the circuit.
So where does this reactance even come from? Well, it's created by things like capacitors and inductors, which are all about storing energy in electric and magnetic fields. But here is the absolute game changer, the most important thing to remember. While resistance is pretty much constant, reactance is not. It changes based on the frequency of the AC current. And that little detail, that's the secret sauce behind so much of modern electronics.
Okay, so if impedance is made of these two things, how do they actually combine? You'd think you just add them up, right? Well, not so fast. It's a little weirder than that. To really get it, we need to visualize it with something called the impedance triangle.
Let's build this thing from the ground up. First, imagine a flat horizontal line. That's our resistance. It's the real, straightforward, energy-burning part of the opposition. It's our foundation.
Now, what about reactance? Since it's storing and releasing energy, it's completely out of sync, or out of phase, with the resistance. So we draw it as a vertical line, going straight up from the end of the resistance line at a perfect 90-degree angle. And finally, the total impedance, Z, is simply the line that connects the start of the resistance to the top of the reactance. That diagonal line, the hypotenuse of our triangle, represents the true total opposition. It's not a simple sum, it's what we call a vector sum.
And hey, look at that. We've made a right-angled triangle, which means we can use a formula that probably gives you flashbacks to math class. The Pythagorean theorem. Z squared equals R squared plus X squared. This simple equation is the key to calculating impedance.
Okay, that's enough theory. It's cool to see it as a triangle, but let's make it real. Let's see how we can use that formula to figure out the total opposition in an actual circuit.
Honestly, the process is just walking through the formula. Step 1, you find your resistance value. Step 2, you find your reactance value. Then you square both of them, add those two squared numbers together, and finally take the square root of the whole thing. Boom, that's Z, your total impedance. All right, you with me? Let's run some quick numbers. Let's say we have a circuit with 100 ohms of good old resistance and 50 ohms of that tricky reactance. So what's the total impedance? And the answer is 111.8 ohms. Now, hold on. Notice that it's not 150 ohms, which is what you'd get if you just added them together. Because they're working at an angle to each other, their combined effect is actually less than their simple sum. That right there is the core idea of impedance in action.
Okay, so we've covered the what and the how.
We know what it is, we know how to calculate it. But the biggest question of all is, why? Who cares? Why is understanding impedance so unbelievably important in the world of electronics?
Well, here's why it all matters. Because reactance changes with frequency, engineers can use impedance as an incredibly powerful tool. Think about your speakers again. They build circuits that have a low impedance to low frequency bass sounds, letting them pass through to the big woofer, but a high impedance to high frequency sounds, blocking them. And a radio tuner? It's the same idea, just in reverse. It's designed so the impedance is super low for only one frequency, the station you want to listen to, while acting like a brick wall to all the others. From power lines to antennas, controlling impedance is how we control the flow of AC power and information.
So the big takeaway here is this. Don't think of impedance as just an obstacle. It's a precision tool. It's a lever. Because you can tie it to frequency, you can design circuits that are basically invisible to some frequencies, but are a total roadblock to others. That's the magic behind tuning a radio or filtering audio. So I'll leave you with this thought. What else could you build, what else could you control if you could precisely manage the flow of any frequency you choose? That's the real power of impedance. Thanks for joining me.
Thanks for watching.